So we finished up infinitely repeated games, and so now we'll take a look at those games where, it's a game that doesn't go on forever, but it could also be a game that we know is going to end at some point. We just don't know when. Okay, and so that's the aspect of a finitely repeated game. That is, we know there's an end, right? So, for example, there's an end to the semester. Actually, and you know exactly what it is. But a lot of times, if businesses are competing against each other, right, they know at some point, maybe somewhere down the road, some business goes out of business, right? And so you're no longer competing against the other person. But a lot of times, you just don't know exactly when that is, okay? So, finitely repeated games. These are games that don't go on forever. But each player doesn't exactly know when the game ends, okay? Now, again, there are some games where you know exactly when it ends, right? Like the end of the semester. That is a finite game, and you know when it's going to end, okay? But for the games where, when companies are competing against each other and they're not quite sure when it's going to end, what we do is we say, okay, look, there's some probability, and we'll use the term theta, okay? There's some probability that the game's going to end. And then, of course, 1 minus that is that the game will continue, okay? So theta here, our Greek letter, is the probability that the game ends. And we'll say the game ends after this round, right? After the next round, after next round, okay? And 1 minus theta is just the other probability, right? So if there's a 40% chance that the game is going to end after this round, then that means there's a 60% chance, right? 1 minus the 40% chance, right? So 1 minus theta is the probability that the game continues, okay? So if theta is the probability the game ends, 1 minus theta is the probability that the game continues, okay? All right, now let's, actually I think I took up all the space there. So actually I'm going to move this. Let's see if I can move this. Can I lasso this? Let's move this up top. Yeah, that didn't work. Okay, come on, lasso. Let's try this again. There we go. Let's move this up here so it can fit right in there. Okay. All right, because we have to add in a little bit of math, okay? So let's suppose two companies are going to play a game, right? And again, the game we're going to analyze, we're going to go back to the exact same one, the competition versus collusion game, okay? So let's think about if two firms try to collude, okay? And that is they each try to earn, each earns monopoly profits. We'll just do pi m. Okay, that's a bad m. Pi m to indicate monopoly profits, okay? Okay, so if we think about that, for each firm, what's the expected value of colluding? And we'll just do COLL again like we did last time for colluding, okay? Well, it's going to be the profit you make when you collude the first time, okay? You play the game once. But you don't know if the game's going to continue, okay? So it's going to be the profits you'll earn next time, but you have to multiply that by the probability that the game continues. So 1 minus theta, okay? And then the third time, pi times, now again, this is 2 times away, so you just square the probability. So this is 1 minus theta squared, and so on, right? So the expected value of colluding is again going to be this sum that goes on forever, but again, it has to do with here basically the probabilities, okay? Okay, so this means we basically have pi times, and again, you can write it this way, but this is n equals 0 to infinity of 1 minus theta squared. Okay. Now, again, you can keep it in this form, or you can use the ninth mathy form, which I've done. Not squared, sheesh. This should be n. Because the nice thing about this nice mathy form is that if you remember from your sequences and series long ago, the sum of, from n equals 0 to infinity, of r to the n is equal to, this is actually 1 over 1 minus r. Okay, if you simplify it and find what it converges to 1 over 1 minus r, right? Which means this is equal to pi times 1 over, now 1 minus, now r, remember, is this term in here. So r for us is 1 minus theta. So this is 1 over 1 minus 1 minus theta. Okay? So that means it's pi times, well, 1 over 1 minus 1 plus theta, which is equal to just pi over theta, okay? So that's what you can use to kind of solve these types of problems, right? The expected value of colluding, that is being able to collude for some unknown amount of time, is just the profit you're going to make divided by the probability that the game ends. Okay, so it's a nice simple way to think about it. Okay, so let's work through this one, right? This is the exact same problem that we had before, right? We know that our dominant strategies in Nash equilibrium were such that firm 1 has a dominant strategy to do low price, and firm 2 has a dominant strategy to also do low price, right? So we've gone through this game before. We know this is our Nash equilibrium and so forth, okay? So the question is, when will the firms, again, given that this is now a game that is going to end, but you just don't know when it ends, when will the firms collude and achieve this outcome down here in the lower right, and when instead will the firms compete and achieve the Nash equilibrium outcome here, okay? Well, we're going to assume they use the same grim trigger strategy we talked about before. So that is, we have to basically say, okay, they will collude when the expected value of colluding is greater than the expected value of cheating, because then thereafter they're going to make 0, right? They end up back at this Nash equilibrium point, right? Well, let's think about each of these. First, let's do the expected value of cheating. So if they cheat on the collusive agreement, expected value of cheating, and actually I'm going to start to run out of space. So let's go to the next page. Okay. So I've got, what I'm trying to show is that they will collude if the expected value of colluding is greater than the expected value of cheating on the other kind of collusive person and then being stuck at the Nash equilibrium, okay? So we'll put cheat down here, okay? So, well, the expected value of cheating, this is pretty easy. So let's flip back to this game. Remember, if a firm cheats once, they get that massive payout. They get the $50 million payout. And then after that, the other firm says, well, you can't be trusted. I'm going to go back to the Nash equilibrium outcome, okay? So this one's easy. Expected value of cheating is you get 50 million once, and then after that, it's just a sequence of zeros, right? So you're going to get in total 50 million, okay? But now, colluding, if they're able to maintain this monopoly outcome and collude, then they get 10 million each time they play, okay? And we know the way to find the expected value of colluding, right, is equal to that payout they get, pi, divided by the probability that the game ends, right? That's just what we kind of demonstrated the slide previous, right? Okay, well, this profit, this payout, is the 10 million. So the expected value of colluding is equal to 10 over theta, okay? So 10, now let's, right, again, our original expression is this one right here, right? So that is the expected value of colluding. Again, for them to collude has to be greater than the expected value of them cheating. Okay, so now we can put in the figures. This is 10 over theta is greater than the expected value of cheating, which is 50 million. Okay? All right, so now multiply, actually, these are both in millions, so we don't need that there. So multiply now by theta, 10 greater than 50 theta. Move this up here. Now let's divide by 50. That means theta is less than 10 over 50. Okay? Which means theta is less than 1/5. Or a probability of 20%. Theta less than 20%, right? 1/5 is equal to 0.2. Okay, so that means collusion, if I could spell collusion, collusion does not have two S's in there. Collusion can be maintained if the probability of the game ending, that is theta, is less than 20%. Okay? That is, if the game seems like it's going to go on for a really long time, then it makes sense for them to collude because over time they can end up making higher monopoly profits, right? But if instead that theta is really high, that is, there's a high probability that the game ends, then yeah, there's going to be more of an incentive for one of the firms to cheat on the other firm, take that $50 million payout because they know the game is going to end pretty soon, okay? So that's how you would work through and think through a finitely repeated game, okay? Now, before we wrap up this video, let's talk about an additional idea that relates to games that we know are going to end, right? And this is what we call the end of period problem, right? So this is the problem that arises when everyone in the game knows when the last period is, okay? So as the top part here says, suppose players are playing a game, and each player knows exactly when the game will end, okay? So the question is, what's the likely outcome, okay? Now to think through this, you actually have to use what we call backward induction. That is, you start at the end and you work backwards, okay? Now, the end of period problem basically says, the gist of it, and I'll kind of walk through it, but it basically says outcome will be just the Nash equilibrium outcome, okay? Right? And again, the way to think through it and use backward induction is to say, okay, let's suppose I'm in the last period, and I'm a self-interested person, and I know this game ends in the last period, right? Then I'm going to do kind of what game theory predicts and play my dominant strategy and try to get the maximum payout I can get, right? Well, if I know I'm going to do that in the last round, let's go to the round previous to that, okay? Well, if I know I'm going to play the Nash equilibrium in the next round, right, then I'm going to do the same thing again, and we can kind of work backwards to the beginning, right? That's how you use backward induction, right? So the end of period problem basically says, look, if it's a game and there's a known ending and everybody knows when it ends, the outcome is just going to be the same as if you played the game once. That is, it'll just be that Nash equilibrium outcome, okay? Now, what are some real-world examples of the end of period problem? Well, I mean, there's lots of things in our life that kind of come to an end, like school, hopefully coronavirus, right? And so we can kind of think through some real-world examples of this. So two that I have or that come to mind. One is when you're working and you've decided to leave your company, right? You're going to leave and take another job. So you're going to leave company and take another job. right? So you submit your 2 weeks notice. 2 weeks notice. Okay. Now, having given 2 weeks notice before, I can tell you it's great because the end of period problem is great for the employee, right? Because I have zero motivation for those next 2 weeks to do any sort of work for the company I'm currently working for, right? I'm done. I like nothing, no work I do is going to really benefit me, right? And the company knows this, right? And so this is why it's very oftentimes the case that when you give your 2 weeks notice, the company just says, okay, look, just stay home, just go look for another job, we know you're not motivated, right? And so that's an example of the end of period problem, right? I know the end is 2 weeks away, and I have zero motivation to work hard the rest of those 2 weeks, so I behave as if I would on the last day of work, right? So that is, I have employee has zero motivation to work for those 2 weeks. Okay, so let's think about another example, which I think may be a little more comical. Now, we're getting to the end of the semester, and you guys have your evaluations of me, right? And they are due right before final exams, right? So we also have an end of period problem, right? So you're probably going to give me glowing evaluations, like he so smoothly handled the transition to the coronavirus, everything going online. So you give me glowing reviews, and then that ends, and now final exams come up, right? And for me, I'm like, well, heck, they've already filled out my evaluation, so I can give them a really hard final exam, right? I know when this game particularly ends, right? But if we use backward induction, then you could essentially say, well, I know he's going to give me a hard final exam because it's the end of the game, so maybe I should work backwards and give him a scathing evaluation for his teacher evaluation. So that is a goofy example, but also teacher evaluations. And you could also think about the final exam as kind of an end of period problem. Teacher evaluations and final exams. Okay. These are, again, examples of kind of things that end, and the ending affects our behavior as we lead up to it. Okay. Okay, so that's it. The next video we will dive into the final topic, which is going through and analyzing sequential games.